We're going to be looking at elastic potential energy, which is also known as strain energy. So elastic potential energy is the energy that is stored in a deformed material. So that's a material that's either been stretched or compressed. So it's equal to the work done by a deforming force. And it's found by the area under a force extension graph. And if we have a material that obeys Hooke's law, then the force extension graph gives a straight line through the origin. And so to determine the elastic potential energy, which is the area under this graph, it will be the area of the triangle. So that is a half base times height, which is a half multiplied by the extension multiplied by the force. So it's a half Fe. And as the material obeys Hooke's law, then the force equals Ke, where K is the force constant. So if we substitute this equation for force into the equation for elastic potential energy, we will have a half Ke times E, which will be a half Ke squared. And as K, the force constant, is a constant for a given material, then the elastic potential energy is proportional to the extension squared. And what that means is, if we double the extension, so we have 2e, because of the extension squared term, we're going to have 2 squared, that is 4 times the elastic potential energy. And if we have 3 times the extension, we'll have 3 squared, which is equal to 9 times the elastic potential energy. So elastic potential energy is found from the area under a force extension graph. If the material does not obey Hooke's law, so for example material A, then we can see that the area under the graph for material A is less than the area under the graph for material B that obeys Hooke's law. And material B that obeys Hooke's law, its elastic potential energy will equal a half Fe. So for material A, elastic potential energy will be less than a half Fe. In this case, the area under the graph for material A is greater than the area under the graph for material B, which obeys Hooke's law. And so the elastic potential energy of material B, which will equal a half Fe because it obeys Hooke's law, then the elastic potential energy of material A will be greater than a half Fe. If we look at the energy transformations for a spring that is initially compressed and then released and then jumps to maximum height h, then elastic potential energy of the compressed spring is converting into kinetic energy when it's released, which is then converting into gravitational potential energy as the spring gains height. So we can say our elastic potential energy will equal our kinetic energy when it's released, which then converts to gravitational potential energy. And this is also assuming that there's no energy loss, heat loss due to friction. And it's important to note that we're using this equation based on the assumption that the spring obeys Hooke's law. So if we was to double the compression of the spring, so because of the E squared term, we will have 2 squared, so that is 4 times the elastic potential energy, so 4 times the kinetic energy, and so 4 times the gravitational potential energy. So the maximum height the spring jumps to will increase by a factor of 4. Now look at the energy transformations for a bungee jumper. So from the initial jump to the cord unravelling, then gravitational potential energy is converting into kinetic energy. As the cord is unravelling, it's not being stretched, there's no elastic potential energy. However, when the cord begins to stretch to when it momentarily stops, then the gravitational potential energy and the kinetic energy is converting into elastic potential energy. So gravitational potential energy because the bungee jumper is losing height, and also the bungee jumper is decelerating, slowing down, so it's losing kinetic energy, and the cord is stretching, so it's gaining elastic potential energy. So from the initial jump to when the bungee jumper momentarily stops, we have the initial gravitational potential energy converting into elastic potential energy. So the loss in GPE equals mgh, where h will equal the original length of the cord plus the extension of the cord. And that loss in GPE will equal the gain in elastic potential energy, which is a half k E squared. And it's important to note that we're using this equation based on the assumption that the bungee cord obeys Hooke's law. It's important to note that when the bungee jumper momentarily stops, the tension in the cord does not equal the weight of the bungee jumper. We can use this equation to determine the tension in the cord, the deforming force on the bungee cord. So that force will equal to 2 multiplied by the initial gravitational potential energy divided by the extension E.